Hi. So last time we took a look at the Fundamental Theorem of Calculus Part 1, also known as FTC1, and we saw that it relates the ideas from differential calculus with the ideas of integral calculus, which we have been looking at. So let's just do a quick recap of what FTC1 was all about. So FTC1 involved taking the derivative of certain functions, but these functions were defined in terms of integrals. So we could write them as the integral from some a to x f of t dt. And we saw that when we take the derivative of such functions, we get back the integrand, this function f, but now evaluates it at the upper bound. So we get back f of x. So you see we've got this cancellation behavior between the derivative and the integral. Now, when the upper bound is simply x, then this is very straightforward. And we saw that if the upper bound was something a bit more complicated, like some function of x, we saw that you can do a simple substitution and then use the chain rule to make things simple again. Okay, so that was a quick recap of what we covered last time. So this time, we're going to look at the Fundamental Theorem of Calculus Part 2, also abbreviated as FTC2. So the Fundamental Theorem of Calculus Part 2, or FTC2, continues with this idea of relating differential calculus with integral calculus, but in another form now. So just a quick recap. Yeah, so we need this recap before we can continue on the idea of a definite integral. Remember, we defined the definite integral. We just used this notation with this elongated s, with lower bound a, upper bound b. We took this function f, and we said that this was just some notation for the limit as n goes to infinity of the sum from I equals 1 to n, f of x r delta x. Okay, so we wrote this definite integral as the limit of a Riemann sum. We've got this on the right-hand side here. So this is the limit of a Riemann sum. Okay, now if we had polynomials, or should I say simple polynomials, like linear functions, quadratic, up to cubic, then this right-hand side could be evaluated within about a page. I think those previous examples were roughly a page long. Okay, but they're doable. However, if you have other functions, like maybe log functions or exponential or trig, then this right-hand side gets pretty difficult to evaluate. Okay, so what we're looking for is a different or easier method for calculating these definite integrals. Okay, and that's given to us by FTC Part 2. Okay, so let's get into what this means. So if our function f is continuous on AB, sorry, that's in AB, then the integral from a to b, f of x dx, so this definite integral is equal to capital F at b minus capital F at a. Okay, so what is this capital F? Where capital F is any antiderivative of f. Okay, so we see that FTC Part 2 gives us an alternate way of calculating definite integrals. So you can either use this previous way of the limit of a Riemann sum, or using FTC part 2, we can use this way, where we calculate the definite integral as the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. Now, I underlined this any because it says that we can take any antiderivative, but you should be thinking to yourselves, well, if I can take any antiderivative, is this actually well-defined? Because if you take your favorite antiderivative, you might get some answer. But if your friend takes a different antiderivative, they might get a different answer. Because remember, the antiderivative is not unique. Okay, so if I give you some little f and I'll ask you to find the antiderivative, what I'm actually asking for is the family of antiderivatives. Okay, there's more than one. However, remember from last time, the antiderivatives only differ by a constant, by an additive constant. So recall each antiderivative in a family of antiderivatives is different by, well, let's say an additive constant plus c. So if you have an antiderivative and I have an antiderivative for the same function little f, then they are different by some additive constant plus c. Okay, so let's actually see now if this is well defined. So I'm going to choose a different antiderivative, okay? And we're going to see, do we get the same result? So let's try that. So we're trying to calculate the same definite integral. The integral from a to b, f of x dx is equal to, now I'm going to choose a different antiderivative and we're going to see what happens. So remember, we have the antiderivative evaluated at the upper bound, but now I'm going to choose a different one, which means it is different by some constant plus c. Okay, that means I've chosen something different. Minus the antiderivative evaluated at the lower bound. Again, it's different by plus c. And that's equal to f at b plus c minus f at a minus c. Now we've got a plus c, we've got a minus c, that goes. So we're left with f at b minus f at a. And this is exactly what we had over here that we started with. So you see that it doesn't matter which antiderivative you choose, you're always going to get the same answer. In other words, this plus c doesn't matter. So I'll put in quotes here, the plus c for definite integrals. So definite integrals doesn't matter. We will see later on when we do the things called indefinite integrals, well, then it does matter. But for now, it doesn't matter. So if it doesn't matter, well, we could just choose c to be equal to 0. In other words, we choose a particular antiderivative where the c is 0. So we choose a particular antiderivative. Okay, so remember, the theorem works for any antiderivatives, but for the sake of simplicity, we can choose c to be 0. In other words, we chose a particular antiderivative. Okay, now just a tiny bit of notation before we get into the examples. So notation. Okay, it's not too bad. We have that the definite integral from a to b, f of x dx. We wrote this as just f at b minus f at a, but with this bit of notation, we put an intermediate step. Okay, so we write square brackets, we put in our antiderivative, square brackets, and then at the bottom we put a, and at the top we put b. So what this notation means is that we take the function inside, in this case the antiderivative, we evaluate it at the upper bound, minus we evaluate it at the lower bound. So that's just what this notation means. There's nothing too special about it. It's just a little intermediate step that we put in between. Okay. So let's just highlight here this whole idea of putting this angle brackets here. Sorry, not angle bracket, the square brackets with the upper bound and the lower bound. That's just notation. Okay, there's nothing too complicated about that. Okay, we'll see that it's useful notation when we are doing calculations. Okay, because it allows us to write the antiderivative first, and then we can do the evaluation. Okay, so it's a little halfway step there. Okay, so let's take a look at some examples. Okay, so example number 1. Let's calculate the integral from 0 to 1, x squared dx. Okay, we want to calculate this definite integral. So this is pretty simple. So we could use the old way of using the limit of a Riemann sum, but now we're going to try doing it the new way, using FTC2. So what we do is this little halfway step, put the square brackets from 0 to 1. Now we need to find the antiderivative. So let's just make a little note on how we find the antiderivative of some little power function. So remember, if we have x to the n and we want to find the antiderivative, we have to add 1 to the exponent. So if it was n, the new exponent is n plus 1, and then we divide by the new exponent. Okay, so in this case, x squared, the exponent is n. We add 1 to the exponent, so now it becomes x cubed, and then we divide by the new exponent, so we divide by 3. So this becomes 1/3 x cubed. Okay, so that's the halfway step done. Now we can do the evaluation. So first we evaluate at 1, so it's going to be 1/3 of 1 cubed minus we evaluate at 0. So 1/3 of 0 cubed. Okay, now 1/3 of 0 cubed is just 0. 1 cubed is 1. So we're just left with 1/3. Okay, and that's the answer. Now, just as a little note for some practice, try this using the limit of a Riemann sum and see if you get the same answer. Okay, so try that out, see what you get. You should also get 1/3. Now, the nice thing about this method is that if you were to use the limit of a Riemann sum, it might take you half a page to a page to do the whole calculation. Here we did it in 3 lines. So much better to do it this way. Okay, let's try another example. So this is example 2. So let's calculate the integral from 0 to 2 of 2x plus x squared dx. Okay, so we're going to do the same thing as before. Square brackets. So we want to calculate the antiderivative. So these are just a polynomial, so we can use the power rule for antiderivatives. So the old exponent was 1. There's a 1 here. So if we add 1, the new exponent becomes 2. We then have to divide by 2. And that cancels this coefficient of 2. So it becomes x squared plus the antiderivative of x squared. We did this in the previous example. We add 1 to the exponent to make it 3, divide by the new exponent, and we get 1/3 x cubed. Evaluated from 0 to 2. Now, next step, we take this antiderivative, we evaluate it at the upper bound minus the antiderivative evaluated at the lower bound. So at the upper bound, we get 2 squared plus 1/3 2 cubed minus, and then at the lower bound, we get 0 squared plus 1/3 0 cubed. Now, the second term here is just going to be 0 because we have 0 squared is 0, 1/3 0 cubed is 0. So that doesn't do anything. So we're only interested in this first part. So 2 squared is going to be 4, and then 2 cubed is 8. So we have 8/3. Okay, so we can add these two together. We just need a common denominator. In this case, it's going to be 3. So 4 times 3, that's going to be 12 plus 8/3. 12 plus 8, that's going to give us 20/3. So 20/3. Okay, a bit more work than the previous example, but that's just some basic arithmetic there. It's really not too complicated. But you see that this method is still much better than using the limits of a Riemann sum. Okay, provided that you can find the antiderivative. So just a little emphasis here. Please go over your antiderivatives. Okay, so we did go over some antiderivatives before, but please make sure you are very familiar with antiderivatives because all of this integration from now on is going to be done using antiderivatives. Okay, so the first step here, whenever you're doing the integral, is always what is the antiderivative? So it's very important that you are comfortable with that. Okay, let's take a look at one more example. Okay, this is example 4. We have the integral from 0 to pi/2 of cos x dx. Now, doing this using the limit of a Riemann sum, that's going to be quite difficult. So what we do instead is use FTC part 2. So we need the antiderivative of cos, and that is going to be sine. So why is sine x the antiderivative of cos? Well, because the derivative of sine gets us back to cos. So let's just make a little note here. Whenever you want to check the antiderivative, remember that capital F prime needs to take us back to f. So in this case, the derivative of sine is cos, and so that works. Okay, and then we need to evaluate this between 0 and pi/2. Okay, so we have sine of pi/2. So that is the antiderivative evaluated at the upper bound minus sine at 0. That is the antiderivative at the lower bound. So sine of pi over 2, you can think of it as sine of 90 if you need to. That's just going to be 1. Sine of 0, that's 0. So that is a 0. Okay, 1 minus 0, that's just 1. So we see that the definite integral from 0 to pi over 2 of cos x is 1. Okay, so you see when finding the definite integral using this method, it's always the same steps. So step number 1, you find the antiderivative of the integrand. So that's this portion over here. Okay, once you've done that, you can then take your antiderivative, evaluate it at the upper bound. That's this number here. So that's the upper bound. Subtract the antiderivative evaluated at the lower bound. So here is the antiderivative evaluated at the upper bound. Here is the antiderivative at the lower bound. Here we take upper minus lower. And then step 3 is just simplifying if you can. Okay, so if you got fractions that needed to be added or subtracted, you just simplify that as much as possible. And then we get our answer. Okay. So that's it for today. I just wanted to introduce the idea of FTC Part 2. In the next lecture, we will be going through the proof. Okay, that's important to know where these things come from. And then we will be doing some more examples and then getting into the idea of indefinite integrals. Okay, so just before we go, a definite integral is when you have this over here. So what we've been looking at. So we go from some lower bound to some upper bound. We call that a definite integral because we get some number in the end. So it's a definite number, hence definite integral. Later on, we will look at indefinite integrals, which is similar idea, but there the output is another function. Okay, so it's an indefinite integral. Okay, but they are very closely related. Okay, but don't worry too much about that now. We will look at that next time. Okay, as always, if you have any questions, please feel free to email me. You've got my email address, or post a message on our class WhatsApp group. Okay, and then I will try and respond as soon as possible. Okay, remember that we've got the tutorial coming up. If you do have any questions about that, please feel free to ask during our session. Okay, and then we are starting our assessments. So on Wednesday, the 23rd, that's tomorrow, we will have our first tutorial quiz for those that are registered. If you're not registered yet, please let me know as soon as possible before the quiz, and then I will have to put you on a list of students that were unable to attend quiz 1, and then you're going to have to do a quiz later on in the semester. Okay, but that is only for the students that are not registered, and email me. If you don't email me, I don't know if you registered or not, and you're going to have to get the default mark of 0. Okay, because remember these online quizzes are automated. I can't do anything about that. Okay, but if you email me, we can make a plan about moving your quiz to later on. Okay, I will see all of you next time. Bye, everyone.